Hi you guys, today we're going to be talking about the ellipse, the second of our 4 conic sections, and one of the first things that I would like to show you, you see on the screen here, this is National Statuary Hall in the Capitol, and this is actually an elliptical shape building. So we're going to learn about ellipses, but here's the really cool thing about this building. There are 2 points in this building where let's say you go there with a partner. You stand on one point, your partner stands on the other point, and we're talking about hundreds of feet away, and you can whisper, and the person on the other point can hear you. It's very, very cool. So those points we're going to learn right now actually are called foci, okay? And they are actually how ellipses are created. So let me show you exactly how this works. What I have here is a couple of paper clips that are attached to a piece of paper, and those paper clips are fixed at these 2 points. Right now they're arbitrary points, but you will see that they actually have meaning in a little bit. And there's a string that goes between both of them. So I think that you all can agree that regardless of how I move the string stays the same length. So again, the foci, plural for focus, they have a very important job. They are the way that ellipses are created, and so let me show you how. What I'm going to do is I'm going to take the string and I'm going to stretch it around with my pen and stretch it around in different ways, right? And you'll see, so here we go, I'm going to have to kind of switch it up here for a second. What happens is, whoops. Okay, what happens is an oval or an ellipse is created. So it's kind of a messy ellipse, but you can see that that's the shape that is created. So if you have a more precise tool or technologically advanced tool, you can create a more accurate one, or a more clean looking one at least. So here we go. Let's talk about the ellipse again. Alright, so everybody should have their notes out ready to go here. Actually, let me take these away. Alright. So, remember we said that the circle is created by cutting at a horizontal cut. The ellipse is created by cutting on a diagonal cut that's not so diagonal that it comes out of the bottom of the cone. Okay, so we want to make sure that we stay at a diagonal that goes through both sides of the cone. Okay, so here's our plane. And it's good that you guys are getting practice drawing these now, because we're going to do a little art project with conic sections later on, where you have to draw them again. So either you're getting practice now or later, or both. Okay, so here we go. So the shape that's created is this oval, again like a stretched out circle. Just use this pen, which is right here. And like we talked about with the circle, the ellipse can be in any place in the XY coordinate system, but the properties of ellipses are such that one way is stretched out more than the other. Okay, so the longer side of the oval, so in this case the longer side is this one, that's called the major axis. Okay, so if the major axis is called the one that's the longer one, then I think it's safe to call the smaller one the minor axis. Okay? And again, if we were to put our 2 points, our very important points that form ellipses in here, they would be somewhere inside. Okay, so these 2 points are called the foci, the ones that we just put in there. So F-O-C-I. Again, that's plural for focus. So let's put the other one right there. Okay, so now let's talk about the standard form for the equation of an ellipse. Okay, so here we go. We have 2 conditions just like we did with the circle. One is the center is at 0, 0, and the other one has the center at somewhere other than 0, 0. So we're going to use the same letters that we used for the circle, and those letters again are H and K. Okay, so we have a couple of different forms here. We have x squared over a squared plus y squared over b squared equals 1. And A is the letter that typically denotes the major axis. So if you have a bigger number in here for A, then that means that the oval is going to open up longer along the x-axis. Okay? But you could also have x squared over b b squared plus y squared over a squared equals 1. And this time, because the a is underneath the y, that means that it opens up in the long direction, in the y direction. Okay, so maybe we should make a note of that here. So this one is longer in the x direction because of the fact that the a is directly underneath the x. This one is longer in the y direction because of the fact that the a is directly underneath the y. So a denotes major or longer axis. Okay, oops, I just realized that you couldn't see. Okay, just like we had yesterday with the circle, what we're going to do to find the equation for an ellipse with a center somewhere other than 0, 0 is x minus h squared over a squared plus y minus k squared over b squared equals 1. Okay? So same thing as what we have over here. Because the a is directly underneath the x, this one opens up longer in the x direction. Okay? And then it can work the other way as well. X minus h squared over b squared plus y minus k squared over a squared equals 1. So as long as you remember this format, that it's x squared over either a squared or b squared, y squared over a squared or b squared equals 1. It always has to equal 1 on the right-hand side for ellipses. And you understand that if you have something added to or subtracted from the x or the y, that you have a center somewhere other than 0, 0, the properties are very similar to circles. Okay? One last piece of information is the distance from each focus to the center of the ellipse. Okay, so let me draw an ellipse down here. So again, these are the foci, and let's say that the center of this ellipse is right here. Okay, so we need to know how to find this distance. Okay, and we're going to call that c. So are you ready for this? This is kind of trippy. Only in ellipses does c squared equal a squared minus b squared. Only in ellipses. Okay, we all remember the Pythagorean theorem is a squared plus b squared equals c squared. In ellipses, it's backwards. It has its own set of rules. Okay, so this again is used to find this distance from each focus. Again, that's singular for foci. To find the distance from each focus to the center of the ellipse, we use this equation. So if anybody is interested in that, I will definitely show you in class where that is derived from. But other than that, take my word for it. Okay? So everybody switch over to the next video. We are going to start on our examples.